Hello and welcome to a new video on the CryptoTool YouTube channel in the Let's Break It series. This video is about distributed cryptanalysis. The video is structured into different parts. In the first part, we will have a look at the motivation and why it's a good idea to perform distributed cryptanalysis instead of only cryptanalysis with a single computer, for instance. Then we will have a look at how distributed cryptanalysis with a peer-to-peer network works. Then we will have a look at CrypCloud. After that, we will have a look at Klaus Schmeh's DES challenge that he created in 2019. And finally, we will have a look at how to perform distributed cryptanalysis with CrypTool 2. Brute force attacks on modern ciphers need a lot of computing power. And as an example here, a single computer could, for instance, search for years for a symmetric key. And with 128-bit ciphers, a single computer could search for millions of years. And a computing cluster can speed up the search for such a key, since brute force attacks can be performed in parallel. So you can divide the key space into different parts and then let each of the computing cluster nodes compute a part in parallel, and in the end you combine the results and that gives you a nice speed up. And here's an example for that. Let us assume that a single computer can do an exhaustive search for a key of a cryptographic algorithm in, for example, 4 weeks. And clearly then, 2 computers can search for the same key in about 2 weeks. And 4 computers then can search this in about 1 week. And then when we have 8 computers, the search is only about 3 days. Already with 16 computers, the search is only about 1.5 days. With 32 computers, the search is only about 3/4 of a day. You see where we are going here. So 64 computers search only in half of that time. So what we see here is that doubling the number of computers for cryptanalysis, or for every parallelizable computing problem, divides the search or the computation time by 2. Now we have a problem. A computing cluster is expensive since one needs to buy computers and servers, buy network equipment to interconnect all the servers and computers, then maybe pay administrators for the maintenance of such a cluster, then of course pay for power for the server room and so on. And since not everyone can afford a computing cluster, in the mid of the 1990s, volunteer computing was invented. And with volunteer computing, volunteers donate their free computing power of their local home PCs to a bigger project. And example projects for volunteer computing are, for instance, the SETI at Home project, the search for extraterrestrial intelligence at home, where people spend their home computing power to support this project. Or when we go to cryptanalysis, we have the Enigma at Home project, where volunteers spend their computing power to break original Enigma messages. And most of the volunteer computing approaches we know are based on the Berkeley Open Infrastructure for Network Computing, or abbreviated BOINC. And the idea of BOINC is that costs are shared equally to all volunteers, because a volunteer only pays for his computer participating in the computations. And for BOINC, only a single central server for distributing the work units to volunteers' computers are needed. Then, during my PhD thesis, I got an idea. Why not get rid of the central server? And my idea was to, instead of using a central server, we use a so-called unstructured peer-to-peer network. An unstructured peer-to-peer network you can see here on the right side. So you have different computers, the peers, and they are connected with random connections. So you have no clear so-called network overlay, for instance like with a cord network where you have a nice ring, or with a server where you have a star network. With an unstructured peer-to-peer network, peers are just connected in a random overlay. And I developed different distribution algorithms for distributing cryptanalysis to such a peer-to-peer network. And we also implemented one of these in CrypTool 2. And this is called the CrypCloud and the key searcher. And we developed a C# library for peer-to-peer distributed computing, which we named VolunLib2, which is the core behind our peer-to-peer network. Now, what is the basic idea of distributed cryptanalysis with a peer-to-peer network? The first idea is that our search space consists of so-called slices. And a slice is equal to a single cryptographic key to be tested in a brute force attack. That means our cryptographic algorithm decrypts our ciphertext using the key, rates the key, for instance, with a cost function, and that's what we mean with a single cryptographic key to be tested. And of course, the correct key gives the best value with respect to the cost function. Then our brute force search is a so-called job. And to finish the job, all slices or keys of that job have to be computed or tested. And we split the job in equally sized subjobs. That means that we have not only a single job over the complete search space, we have different subjobs dividing the search space, and each subjob of course consists also of slices. And to finish such a subjob, one has to finish all the slices of the subjob. And we maintain a best list of so far found best keys with respect to the cost function. And of course, the solution, so the key that we are searching for, will be on top of the best list. And we use a gossip-based network protocol to distribute results of subjobs to the peer-to-peer network. That means that our peers just talk to their direct neighbors and exchange what they have computed so far. But with this basic idea, we have a problem. And now I try to explain the problem with this basic naive algorithm. Let's assume we have a search space of 40-bit, so we search for a 40-bit symmetric key. That means we have 2 to the power of 40 slices or possible keys. Now let's assume that each subjob consists of 2 to the power of 15 slices, so 2 to the power of 15 keys. That means that we have a total of 2 to the power of 25 subjobs that have to be computed. Now let's assume that we spend only 1 bit per subjob to define if it's computed or not. A 0 means it's not computed, a 1 means it's computed. In a data structure, for instance, in a big array, and we have to flood 2 to the power of 25 bits of data. And this means that we have to flood 32 megabyte per network message every time we want to inform our neighbor of updates. And of course we have to flood to our direct neighbors, because without a central server we have to flood the complete state, so the complete 2 to the 25 bit of data every time. And constructing a network protocol this way is impractical, because let's assume we have 1000 peers, then every peer floods, that means we have 32 gigabytes of data every time the network is updated. And so, to solve this problem, we invented the epoch distribution algorithm, short EDA. And the basic idea is that instead of flooding the total computation space between our peers, we split the computation space in epochs, and for each epoch we have a defined number of subjobs. And we use bit masks as a data structure to define which subjobs have been already computed or not. And of course we can set the size of the bit mask in such a way that flooding is possible. And instead of flooding the complete space, then we only flood the current epoch, the epoch ID, and the best list. What does this mean? So we want to compute this total computation space here. We divide it in equal sized epochs, and then we start computing. And peers select random unset bits out of the bit mask. For instance, let's assume we are here in epoch 2. And then they compute the subjob that is identified by this bit. And then they finish the subjob, they set the bit in the bit mask, and they flood the bit mask plus the best list. And when such an epoch is finished, they can throw this bit mask away, then increase the epoch ID by 1 and use the next epoch, or compute the next epoch and use the next bit mask to do so. And of course, when the current epoch is completed, all bits are set to 1, we go to the next epoch. And of course, the algorithm terminates when the last epoch has been finished. So our network goes through the search space epoch by epoch until it has completed computing the complete search space. And of course we have some problems here. For instance, peers select subjobs randomly, and it can happen that collisions occur so that two peers compute the same subjob at the same time. Then they will stop the subjob when the other peer finishes it and informs that he had finished the subjob. But we have also solutions to lower the possibility of collisions. That's the so-called extended epoch algorithm. But this extended epoch algorithm is not part of this video and not implemented in CrypTool 2. But just that you have an idea of the extended epoch algorithm, instead of only having one bit mask, we have two, and we have different probabilities of selection in each of the bit masks. And I showed in my PhD thesis that this can lower the collisions. But right now in CrypTool 2, we have only the epoch distribution algorithm EDA. Now let's come to CrypCloud. CrypCloud is a computing cloud based on a peer-to-peer network created by volunteers. And you can see here the login of CrypCloud in CrypTool 2. So you have a username, a password, and then you can connect. And you can, of course, create a new account, or you can change your password. To log in into CrypCloud, a bootstrap server is only needed for entering the peer-to-peer network. So you might see CrypCloud and say, okay, but it connects at the startup at the server. So you said you want to get rid of the central server. Yes, that's true. But to find an entry node into the peer-to-peer network, that bootstrap server is needed. After you have connected to CrypCloud, and there are many users then in CrypCloud, then it could happen that you also close the connection to the bootstrap server and you are only connected via the other peers, because peers are interconnected to each other also. And with CrypCloud, login is possible as anonymous user or as registered user. And only registered users can create cloud jobs. But to participate, you can just use anonymous. And currently, only the CrypTool 2 key searcher component supports CrypCloud. We will have an example of a key searcher with distributed cryptanalysis brute force job later in this video. And CrypCloud is based on VolunLib2, and it uses UDP as a network protocol. And it uses UDP hole punching to connect over, for instance, routers to other peers. And details on CrypCloud are shown later in this video when I present how it works in CrypTool 2. Now I come to Klaus Schmeh's DES challenge. In 2019, Klaus Schmeh, who is a blogger and a friend of CrypTool 2 and author of several books about cryptology, met Whitfield Diffie, who is also a very famous cryptologist, and you probably have seen him in my video about the Diffie-Hellman key exchange. There I showed a photo, so if you're interested in Whitfield Diffie, have a look at this video. And Klaus Schmeh met Whitfield Diffie at the NSA Symposium on Cryptologic History. And after a talk with Diffie, he realized that we need a new DES challenge. So he created one. DES is a block cipher with 56-bit key space, and today we can search through a DES key space using specialized hardware in less than a day. But Klaus Schmeh was interested if we can speed this up. And so he created a DES challenge where he encrypted a single DES block, and he gave us the ciphertext. This is this block here. This hexadecimal values are the ciphertext. And he gave us the complete plaintext. And the plaintext is Schmeh C2, which stands for challenge 2, I assume. And his question was, how fast can we find the key today with a known plaintext attack? And the record is right now 22 hours. Clearly with CrypTool 2, I don't assume that we can break this record, but I hope that we nevertheless can find the original key. And my question is now, who helps me in finding this key? And all you have to do is to connect to CrypCloud and donate your computing power. How this works, I will show you in a few minutes. And steps to participate in the DES challenge would be, first you have to, of course, download and start CrypTool 2. And then optional, create a CrypCloud user account in CrypTool 2, but you can also use the anonymous user. Then you have, of course, to log into CrypCloud. Then you have to set the number of CPUs for computing cloud jobs in CrypCloud settings. After that, you have to download the CrypCloud job in CrypCloud, which is named Schmeh 2019 DES 56-bit challenge. And finally, you have just to start the downloaded workspace by clicking the play button in CrypTool 2, and the key searching then starts automatically. Now, after we know the basic ideas of distributed cryptanalysis with peer-to-peer networks and CrypCloud, I want to have a look at CrypCloud in CrypTool 2. I'm here now in CrypTool 2 and I want to show you how you can participate in Klaus Schmeh's DES challenge via CrypCloud. And you can find the CrypCloud with this icon here on the top right side of CrypTool 2. You just click this here and then you get a login. If you want to create a new account, you can just click here, create a new account. Then you have to enter your name, email, and 2 times a password. And then CrypTool 2 will connect to a server of the CrypTool team and generate a certificate which is encrypted with your password. Then it will download the encrypted certificate. And for instance, you could connect via CrypCloud on other computers by entering your name and password, and it would use the same certificate. When you want to log in to CrypCloud, you enter your username and your password here, and you can save the login data. The login data then is stored on your computer, encrypted using the Windows password that you have. So the username and password are stored securely. After entering the username and password, you can just click here on Connect. Then after some time, you see some jobs here pop up. So for instance, we have a Do Not Join test job here, or we have the Schmeh 2019 DES 56-bit challenge. And then you can open the challenge by clicking on that. But before we go to the challenge, I want to show you how you can change the number of CPUs you want to spend for cloud computations. For that, you go here to the settings. In the settings, you can open General Settings and then CrypCloud. And then you can choose here the amount of workers. The maximum number of workers is the number of CPU cores you have in your machine. And you can enable OpenCL to allow the GPU also work in the cloud for you. Now let's go back to CrypCloud. We are now back in the CrypCloud job list, and you can click, for instance, on a job, and then you see some information. A job has a job ID, a job name, and you see the state of the current epoch. That's how many of the subjobs in the epoch that we are right now in are currently computed. An epoch here consists of about 250,000 or 245,000 subjobs. And we have a total of 67,108,864 subjobs in the DES challenge. And here you see also a visualization of the currently computed bit mask. To join a cloud job, you just click here on Open. Then it downloads the workspace. And as you can see here, we have here our ciphertext that we got from Klaus Schmeh, and we have the key searcher here. And the key searcher is set to enable CrypCloud. And you are not allowed, or you could change values here, but then it won't work, because when you change some values here, the cloud workspace is invalidated and you cannot compute using CrypCloud with this workspace here. So you have to re-download the workspace. But let's have a look what we have here. The key searcher searches through all bytes of the DES key, but it ignores the parity bits. So because of that, we have this pattern here. Please only compute 1, 3, 5, 7, 9, B, D, F at the position of the byte here. So that makes that lets the key searcher ignore the parity bits. And then we have here our cost function. We search for Schmeh C2, that's a known plaintext that we have. And we have, of course, the DES cipher here. And when you click on play, the computation starts. And then you can let the key searcher run as long as you wish. And you see here how many blocks are finished. I will stop it right now. You see here the finished blocks of your computer. You see aborted blocks. When you receive the block from another peer that you are currently computing, then you get an aborted block. Then you see how many keys per second your computer is able to compute. And you get a throughput here also, how many megabytes per second your computer computes. And below here, we have a global overview of the job. So you see, for instance, the throughput of the network here. You see the data space size that has to be searched through. So this is 512 petabytes of data. And you see the average size or time per chunk in the network. And of course, you can increase or maximize the size of the key searcher here. And you can let it run. So I would be really happy if you join in searching for the DES key of the Klaus Schmeh challenge. So I would like to break it. And yeah, that is everything that I wanted to show you in this short video about breaking a DES cipher using CrypTool 2 with distributed computing. I hope you liked the video. If yes, please give a thumbs up. If no, you know what to do, give a thumbs down. Also, I would be really happy if you subscribe to our channel. This really helps us to grow the channel to make CrypTool 2 more popular. So, thank you very much for watching and see you in the next video.